Hi, Chris Kuzmal here. We're going to be looking at how we do our test methods by considering what nodes we delete after we've built our tree. Which nodes we delete is going to dictate which one of the helper methods delete would use, but then instead of using delete, we'll use the helper method because the situation will always apply to that particular helper method. In our first case, we do a sequence of insertions of nodes 0, 1, 2, 3, and 4. When I say a node number, I'm referring to the key stored in the node. And so this is what our tree looks like after we've done that sequence of insertions. If we scrub the parent of node 4, then of course node 4 itself disappears from our tree. That is the effect of deletion. And so if we do the sequence of node 4, node 3, node 2, node 1, and node 0, all of those perform a scrub parent function when we would want to delete that node. And so the loop that does a sequence of deletions will count backwards from 4 down to 0. On the other hand, again, we can build up our tree exactly as before, but now what we're going to do is a sequence of scrub parent operations. To scrub the parent of, I'm sorry, excuse me, I misspoke. We're now going to do a sequence of splice out operations. So to splice out node, we can't really splice out node 4 because it's not in a sequence where it has both a parent and a child. So we can't start at node 4. But if we start at node 0, we can splice out node 0, okay? But now we don't want to splice out node 1. That would exercise the exact same code within the splice out because it's removing the root element, and that's a special case. So now what we want to do is splice out node 2, okay? And you'll notice that we would love to splice out node 4, except node 4 is not a splice outable node. It would have its parent scrubbed. But splicing out all the even nodes if the root node is node 0, and if the structure of our tree is of this kind, that is, say, every node has one child because we did a sequence of insertions of nodes 0, 1, 2, 3, and 4, and so on, then that will test only splice out, and that's exactly what our code does. Finally, if we create a more involved tree, and how we create this tree should be the subject of another video or even two, but if we create a more involved tree, which is balanced, like we see here from the insertions in this example of 4, 2, 6, 1, 3, 5, 7, then if we delete element number 2, node 2 here, then that's deleted through the rotate out method, okay? And so the rotate out method could not then delete node 3. It can delete node 4. Now, we can't always delete an even node every single time, but if we delete the node 2, 4, 8, 16, by going up by doubling the node index, the node key, then we'll always have 2 children. And so the next node key to delete is a node with key 4. And so this would be an example of a fairly small test case for rotate out. But you can make a much bigger tree and delete the nodes if the tree's been built so it's like this, then the nodes which have key values of a power of 2, except for the node with a value of 1. Nodes with key value that's a power of 2, 2 to the first, second, and so on, those nodes, when deleted in sequence, will always be nodes which have at least 2 children, and that corresponds to the rotate out method. And so that sequence will test the rotate out method only, and so that dictates what the for loop will look like for the rotate out method. And so those are the 3 different ways we do the deletion sequence in order to test each of our 3 helper methods for deletion. And we'll stop with that.